All right, so with that being said, let's go ahead and take a look at example 1, which is to verify Green's theorem for the following line integral, where C is the unit circle. So if we are to verify Green's theorem, that means we want to calculate the one side and the other side and show that each of these yield the same result. So let's go ahead and start with calculating the line integral directly. So as is. Okay, so they tell us that C is the unit circle. And because we're going to be using this in Green's theorem, where we need the the boundary of the domain to be a simple closed curve oriented counterclockwise, we're going to go ahead and draw this first and just show that we're going to use the standard parameterization that most of you would probably think to use anyway. And that is starting the circle here, tracing it in this orientation. So that's 1, 1, negative 1, negative 1, and that's our domain D. And we'll just say that the boundary of D is C. Okay, so with that being said, we can say that C is parameterized by R of t equals cosine t sine t for t in the interval 0 to 2 pi. Okay? So now, for this line integral here, really what is this saying? It's written in this alternate notation. So remember, we could express this integral. This is the same as the integral over C with this vector field dot dr. So we could represent it like that if we wanted to, but it's written in this alternate notation, which is perfectly fine. So because it's written in this notation, I'm just going to remind ourselves here that really what this parameterization tells us is that this is x and this is y. So really, we've got x equals cosine of t, y equals sine of t, and then we can figure out what dx and dy are. Dx is negative sine of t dt, dy is cosine of t dt. So then we can take this line integral, xy squared dx plus x dy, and go ahead and rewrite this as, I guess I'll go downward, write this as the integral from 0 to 2 pi of our x, which is cosine of t, our y squared, which is sine squared of t, and our dx is negative sine of t dt, plus our x, which is cosine of t, times our dy, which is another cosine of t dt. Of course, we can factor out the dt, writing it like we normally would for an integral, and then let's collect our like terms and see what we have. So we end up having sine, I'm going to write it with the positive term first. So cosine squared t minus sine cubed t cosine of t dt. Okay? So how would we want to compute this? Well, there's a couple things that we could do. This one's a little bit tricky to think about. Let's just talk about it. These are two separate terms, so if need be, we can think of integrating them separately. Two different techniques for two different integrals. If we think of it as separate integrals, so the integral of this one and then minus the integral of that one, we can focus on this one and we can just write this as 1 plus cosine of 2t over 2 and use a half angle identity on it. For this term here, we can do a u sub, with u equals sine. du is cosine of t dt, and that would work. So let's go ahead and do that. What I'm going to do is imagine just kind of, let's go ahead and write this out. So I'll make some room someplace here. Okay. So we'll go ahead and first I'll write it below here since we have a little bit of room. See how much we can fit in here. Might be able to get it all in. So here we'd have 0 to 2 pi, and with the half angle identity, the half angle is cosine squared t equals 1 plus the cosine of 2t over 2. So I can factor out the 1/2 and write this as 1 plus the cosine of 2t dt minus, if we do a u sub on this term, so this would be, we'll do a u sub, I guess I'll do this one in red just to distinguish the different, here this is this term, this is this term. So for that term we'd have u equals sine of t, du is cosine of t dt, which is great because we have a cosine of t dt. So this u sub will work, they'll get a u cubed du. But we have to change our bounds. So u of 0, what is the sine of 0? Well, 0. What is u of 2 pi? Well, it's the sine of 2 pi, which is 0. So this integral ends up becoming the integral from 0 to 0 u cubed du, which is just 0. So whenever you do a u sub on a sine or cosine and your range is 0 to 2 pi, be on the lookout for that. They're periodic, so it would repeat. So that's a common feature that will happen quite a bit. Let's see if we can sneak this final answer in there. If we integrate this, we'll have 1/2 times the quantity t plus a half sine of 2t between 0 and 2 pi. And notice that if we plug in 0 and 2 pi into sine, we're going to get 0 for each of them. So this term is 0 on this interval. So then we'll just have this term becoming 2 pi minus 0, which is 2 pi. So 2 pi is what the bracket becomes. Divided by this 2, we should just have pi. So pi is our final answer for that one. Now, if we're going to go ahead and do this, the method of using the right-hand side of Green's theorem, then we need to know what del f2 del x is. So what's our vector field? Our vector field, so we can say that this is f1, it's the x component, and f2 is the y component. So del f2 del x is 1, and del f1 del y is equal to 2xy. So the double integral over d, actually let's go ahead and describe d first before we do that. So we have that, what's d? So d is this region over here again. It's the unit circle. So the easiest way to describe d would be in terms of polar coordinates. So radially simple region. So I'll go ahead and say that in a radially simple interpretation, this would go from 0 to 2 pi, and r would go from 0 to 1. So the double integral over d, we'd have del f2 del x which is 1, minus del f1 del y, so 2xy, dA. And if we're going to do this in a radially simple manner, then this would become the integral from 0 to 2 pi, the integral from 0 to 1. We'd have to convert our integrand, so this would become 2 r cosine theta r sine theta r dr d theta. Because remember that in polar coordinates, x is r cosine theta and y is r sine of theta. We are no longer referring to x and y right here, because this is the parameterization for the actual circle itself. But what we're doing here is we're changing coordinate systems, and we're talking about the interior here, this area. We're not talking about anymore just the circle. That was part 1. We're now doing the right-hand side, part 2. So once we have it written like this, we'll simplify this. 0 to 2 pi, 0 to 1. This will become 1 minus 2. Actually, I'm gonna go ahead and also take this r and bring it inside, which will make this an r instead of a 1. So we'll actually have r minus r times r times r is an r cubed. So 2r cubed sine theta cosine theta. Now, one thing we could do, well, actually, let's go ahead and do our r integral first. So 0 to 2 pi. If we integrate this with respect to r, we're going to have 1/2 r squared. And this will be minus 2/4, so 1/2 r to the 4th sine theta cosine theta from r between 0 and 1, d theta. Simplifying this, we should just have 1/2 minus 1/2 sine theta cosine theta d theta between 0 and 2 pi. Well, a similar thing is going to happen here. This term, we can just integrate. This will become 1/2 theta, and then we'll plug in our bounds. This term here, we're going to have to do a u sub. The u sub will be sine, and it will work out because du is cosine theta d theta. So our u sub will work, but what's going to happen to our bounds for this term? U of 0 is the sine of 0, which is 0. So the bottom bound is 0. But then to figure out what the top bound is, we need to know what sine of 2 pi is. That's also 0. So this whole term, its integral is 0. So the only contribution we're going to get is from this term. And when we integrate 1/2 with respect to theta, we get theta. Between 0 and 2 pi, we just get pi. So this whole thing does actually give us pi as well. So each of these methods gives the same answer, so we have just verified Green's theorem.